Okay, so to finish up page 3, we just did a horizontal circle mathematically. Let's look at a horizontal circle conceptually. And so previously I said, well, technically there's a vertical component of tension. So some types of problems, especially in AP physics, to minimize that angle down to 0, it's still not even real life. You swing a ball of uniform circular motion in a horizontal circle on a frictionless surface. Does real life have frictionless surfaces? No, we can have slick surfaces, right? The tabletops that you are sitting at is pretty smooth, right? But there is some friction. And so I'm going to try to attempt a 3-dimensional picture. I'm not an artist. So if you think about a table, so here's my 3-dimensional table. Will you accept that as a table? Drill a hole in the center. Oh, the games our physics plays. And then you put a string through it and attach a ball to that string. Now, maybe under the table is where your hand is. Maybe that's you've connected a motor. Maybe we assume there's no friction at the hole. We've got some kind of like greased up system so that it's minimizing friction. Whatever game you want to play, no friction. And that ball is going to be spun in a circle. Now you don't have any angle whatsoever. Okay? You just have to assume it's frictionless. And so it's still a horizontal circle. So I've kind of got a top view of this 3-dimensional table. And it says we're going to spin it with a constant force. And we do need to edit the questions a little bit. I don't know what happened. You know, every year I tell myself I need to go correct this for next year, and every year I forget. What happens to the speed if the force that started out as 1F, they're kind of laying the foundation, 1F, what if we reduce it to 1/2F? What's going to happen to the speed? Now, what should a good scientist do about the mass and the radius? A good scientist only makes one change at a time. So if I'm changing the force, mass and radius need to be constant or same. Now, we played this game of 1, 1, 1, 1, right? Last class, whenever we were learning about centripetal acceleration. And so here it's a force. There's a tension force on the ball. And so if we do a little diagram, it's small, but there's a tension that's center seeking. And so your centripetal force is only due to the tension force, kind of like what we did above. Everybody good? And so centripetal force is that MAC, which what can we plug in for AC? Our new equation for centripetal acceleration. It's the 6th equation on the formula chart. AC equals V squared over R. And so I'm calling it tension in my example, but the force that's exerted on the ball is what they're talking about. And so I've got this force equals mv squared over R. What if everybody starts at 1? Kind of like the example. So is this a true story? 1 times 1 squared divided by 1, it's still equal to 1. Now let's make a change. Now, with constant mass and radius, still 1, 1, what if I have half the force? What's going to happen to the speed? And so I would have F, or let's put in a half there. Mass would be 1, radius is 1, and we're trying to figure out this new speed. And so to get the new speed, you would do square root of solve for V. Square root of 1/2. And so V would be square root of 1/2, which is about 0.7. I'll save us a little time there. Previously, it was 1. Now it's 0.7. So as your force decreases, your speed decreases. And I can kind of demonstrate that. You don't see tension, but me, I feel tension. And so if I start it with a good velocity, good, right? Not too fast, not too slow, but then I tug less. It's going to slow down, okay? But here's a question. Half the force, did we get half the velocity? It went from 1 to 0.7. It decreased, but not quite half. Good deal? And why not? Because it's v squared. You had to do square root. And so v, or speed there, it decreased, but not by half. Everybody good with that? Okay, reset your mind. We're back to the original. 1 times 1 squared over 1 is 1. 1, 1, 1, 1, 1, right? Okay. Now what happens to the speed if the force is doubled? Again, mass and radius got to stay the same, one change at a time. And so now we're going to have 2 equals, same mass, same radius. We're trying to find this new speed. So isolate v. V would equal the square root of 2, which is about 1.4. Now don't go, oh, it doubled from 0.7. This is a different problem, right? And so you got to go back to the original. The velocity was 1. When they doubled the force, did your velocity double? No. But when they increased the force, did the velocity increase? Yeah, that could be a true statement. And so your speed increased, but not by 2. Okay. So this proportion game, and y'all, AP loves the proportion game. They will give you 20 questions like this before they give you one calculation. Plug and chug with the calculator, okay? They want, actually, on the May exam, you may only touch the calculator 2 or 3 times. That's what students come back telling us, okay? But this is the math. This is the stuff that you'll do most often. Okay, in your mind, reset back to 1, 1, 1, 1, 1, right? Everybody's 1. Now what happens to the speed? If you keep the force F same, 1F, so this is back to the original force, but, and here's where we need to edit, the radius is increased to 4R. So again, we started at everybody was 1. Now we're going to keep the same force, 1. Mass had no change. We're trying to figure out the V. Here, what they've changed is the radius. They increased it from our original 1 to 4. So now to solve for V, what do we get? It comes out to 2, because when you solve for V squared, you get V squared equals 4. V would equal square root of 4, or 2. And so when you quadruple the radius, it actually ends up with a double speed, okay? And you can kind of see this in the equation because your velocity and radius, they're directly proportional if you have constant force, right? When the numerator goes up, the denominator has to go up to equal the same force. So hopefully this makes sense, right? Okay. And so, final answer, the speed doubles. And honestly, we can leave it there. It increases, and how much does it increase? It doubles. V and R, V squared and R have that direct relationship. Maybe we add that. V squared and R have that direct relationship. Again, AP loves it when you point out relationships. Okay, questions on some concepts. Playing the proportion game. That was a horizontal circle. The only force working on the ball was center seeking tension. And so that's why I put it equal to F net C. All right, so now let's move on to a vertical circle. So let me get my demo back out, okay? And so now I'm going to do a vertical circle. Now gravity's vertical force. Tension is going to be sometimes the vertical force. Okay, this problem is only going to tell us to look at maybe one or two spots, but we're going to take it further. We're going to look at several spots. So here's what you're looking at. We're just going to hit pause at a couple of places. Now, I want to go on and get into A, determine the minimum speed. It doesn't just say the speed. Right now, I'm doing my best to keep a constant speed, right? So it really shouldn't matter where you go. You should have the same speed. But what if it's not constant? What's this minimum speed about? Well, the video, the loop-de-loop, he had a high incoming speed. And then what does gravity do as objects go up? Gravity's going to slow you down. And so technically at the top of that track, the top of the loop, the car is going slower than it was at the bottom. And so whatever number of the minimum speed you calculate, you got to know what location it's at. If you mistakenly say minimum speed is at the bottom, and then gravity slows you down, what's going to happen to the car? It'll fall. That's not good. Hey, you can kind of go home tonight or today and put water in a bucket. Now, I'm not really going to put water because sometimes things don't always go as planned. So I know it would be more daredevil-y of me to put some water in here. Ooh, I should empty a hole punch. Hold on. I don't want to clean it up. Imagine I have confetti or water in the bucket, right? Have you ever spun water in a bucket? If not, go grab a bucket tonight and try it, right? It's not chilly. It's a beautiful day. A little water is not going to hurt you, right? I just don't want to clean the mess. And so I'm going to spin this. Now, I'm going to spin this really fast, okay? I can test my strength. Look at how super I am, right? But that's not fun. That's not a minimum speed. But maybe, there is something in there. Something fell out, okay? I was below the minimum speed for it to fall out. So minimum speed is, is it going to fall out? No, okay? On the ball and a string, maybe you can see a visual of that. So if I do minimum speed here, I just want to get the tub when it's at the bottom, okay? And if I go too low, it doesn't make the circle. It kind of flops into a non-circular path, okay? On a roller coaster, we'll go safe. Let's say you're on a roller coaster, shock wave, okay? As you go up, gravity's slowing you down. Have you ever been upside down on a loop-de-loop and thought, oh no, I'm gonna fall out. I'm coming out of my seat. Thank goodness the seatbelt is there. But theoretically, water in a bucket, if you do the right physics and have the right force and all that good jazz, water doesn't need a seatbelt. So why do you need a seatbelt on the roller coaster? Now, in this Sue happy, crazy world, is any amusement park going to have a roller coaster without a seatbelt and send you upside down? No, nobody's going to do that, okay? Too many lawsuits to consider. And so, but that feeling of, oh no, I'm coming off my seat, that's a minimum speed. You might think, oh, this is random, it's just me. Oh, it's random. No, it's physics. The engineers hopefully did some physics, right? Who built the ride. Hopefully they passed the AP exam, right? And they designed it to be thrilling because you feel like you're going to fall out, but wait, you don't. Does this all make sense? Tying the ball on a string, water in a bucket, roller coaster, loop-de-loop, right? And so it's all the same physics. We just might call it a different force. And so that's the vertical circle that this is making. It says a 0.15 kilogram ball on the end of a 1.1, because who likes to do 1 meter long cord or string of negligible mass? True story. Cords and strings have mass, but we just want to focus on the mass at the end. Okay, so AP a lot of times will say negligible mass for the rope. And it's swung in a vertical circle. So we have a little diagram. If we know it's vertical, this is a side view technically, right? Determine the minimum speed the ball must have at the top of its arc so that it continues moving in a circle. Basically, inertia carries you across the top, okay? And then B, calculate the tension at the bottom. And so before I solve anything, y'all, we're still forces. Step 1 is still what? Diagram, okay? Always diagram, diagram, diagram. I know we started out with velocity and drawing other type of pictures, but at the end of the day, these are force problems. And so we're going to draw a force diagram at the top and at the bottom, because that's where they said we're going to be solving for. And so I'm going to zoom in there. Paper people, I don't know if you want to put it on the side there. It may not all squeeze in nicely. I'm going to zoom in. So at the top, what forces are acting on our ball? Gravity and tension. So gravity, if you haven't noticed, is always down, right? Towards the center of the earth. The only time you don't have gravity is when you're in outer space. And then there's tension. Now tension can vary. The rule for tension is it pulls parallel to the string. So when you're at the top of the path, the string is below the ball. What direction is this string pulling on the ball? Down. So I've got 2 down arrows. Now you can put them side by side, but I like to tip to tail. What not to do, don't draw one big arrow and say FG plus FT, okay? They are 2 independent forces. One is because of a contact force, one is because of the gravitational field. So 2 arrows, tip to tail, both in the downward direction. Good deal? What about at the bottom? What forces are acting on the ball at the bottom? Gravity and tension, same 2 forces, but wait. Gravity, still FG, same, right? Your weight does not change. The direction gravity's pulling you does not change from top to bottom. However, tension does. What direction is tension pulling on the ball now? Up. Now everybody pay attention. Wake your neighbor up, pay attention to this, okay? Today it's tension, tomorrow it's normal force, tomorrow it's whatever other force. I'm going to draw tension bigger than gravity at the bottom, and it's actually also bigger than the tension at the top. There's a reason for it. And so put a star here. Here's what I'm going to say. Tension is bigger than your weight at the bottom. And here's the overarching big idea. We want this ball going in a circle, yes? In order to go in a circle, watch this. Center seeking forces need to be bigger than center opposing forces. Does that make sense? If you want to go into a circle, something has to pull you into that circle. And so you want that pull center seeking force, whatever it is, to be bigger than whatever's trying to make you leave the circle. Because if gravity wins at the bottom, what happens? If the string breaks and gravity wins, are you going to make the circle? No. And so that's a big idea. No matter what kind of force it is, your center seeking forces need to be bigger than center opposing forces. Okay, bonus diagram time. Bonus, what about the side? What about the ball on the side? Same gravity and tension. Gravity always straight down towards the center of the earth. But when it's on the side of the vertical circle, what direction is tension pulling it? On this picture, it would be literally to the right. How big do I draw it? Well, technically, if I have a minimum tension at the top and a bigger maximum tension at the bottom, it's somewhere in between, okay? And so, doing my best here, somewhere in between. But it would be to the right. If we drew it on the right-hand side, tension would be to the left. Okay? Notice a difference too with gravity. On the sides, the gravitational force is perpendicular to the tension force, but it's tangent to the motion at that moment. When it's on the left-hand side, maybe it's going up or down, right? And so you've got that vertical direction here, but that's not part of the circular motion. It's not center seeking, it's not center opposing. So gravity is going to speed it up or slow it down right there. But when it's on the other two, top and bottom, on this axis, it is center seeking or center opposing, okay? Moral of the story, when it's on the side, gravity affects the linear velocity or acceleration, right? But it doesn't affect the centripetal. Your centripetal direction is center seeking or center opposing. Okay, diagrams, check. Step 2. Step 2, after a diagram, F-net statement. And so A talks about the top. Now, by the way, not all problems will say minimum speed at the top. You have to know the problem, ball and string here, okay? Gravity's gonna slow it down at the top, okay? So they won't always tell you the top, but here they do. And so we're gonna write an F-net statement for centripetal motion at the top. And maybe we need to remind ourselves, what's the positive direction for centripetal motion? Y'all remember the defined positive direction? Center seeking or opposing? Seeking. And so notice at the top, both tension and gravity are pointed to the center. They're both going to be positive. And so I'll say FG plus FT. And that makes some of you feel weird that gravity is positive, but it's how your direction is defined. Okay, we're looking for speed. Which of these forces is going to contain our speed? Well, it's not weight, it's not tension. F net equals mass times acceleration. And since we're moving in a circle, it's centripetal acceleration. I still don't see speed. Our new equation for centripetal acceleration, what can I plug in? 4 v squared over r. So there's the speed that we're looking for. Let's keep going. Equals, what can we plug in for FG? mg, weight, is your mass times the acceleration due to gravity. And then tension doesn't have its own equation. And so just plus tension. Wait a second. They gave me the mass. They gave me the radius. We know gravity. Did they tell us the tension? Okay, let's have a concept talk. Remember earlier I said that inertia carries the ball across the top? Okay, when you are riding upside down in that roller coaster, you feel like you're going to fall out of the seat. You might even feel, oh, am I sitting? Am I not? You might just be tangent touching the seat, but you're not pushing into the seat. The seat's not pushing into you. water in the bucket. Maybe it doesn't fall out, but maybe it's not pressing into the bucket, okay? Moral of the story, here's your concept. It zeroes out. Tension at minimum speed, it minimizes to zero. When you're riding that roller coaster going upside down, maybe there's no strings, but the seat pushing on you minimizes to zero, FN. Okay, I wish they'd interviewed that guy doing the loop-de-loop. He should have felt like he was going to fall out, and it happens really quick. So if you're not cognizant to be aware of it, you may not even notice. But I know I've been on roller coasters, and at the top, it's like, ooh, okay. And moral of the story, y'all, I've said this before, if they don't give you tension, can we all make up our favorite number? No, the only number that we could all make up is basically zero, right? But there's a reason for it. It minimizes. Okay. So now we can, oh, look, now I have mv squared over r equals mg. Now, even though I know it, what could I still do? I can cancel mass out. And so to solve for v, I got to multiply both sides by r and then take the square root, yes? And so gr square root. There's our working equation. That's the physics before the math. All right, now it's plug and chug. Square root, I'm going to go with 10. Now some of you are like, isn't it negative 10? Remember, the sign is dependent on how we define the positive direction. And so I defined it center seeking positive, as most people do. Gravity was center seeking. So we've already made the force positive. We've already done that. We're using the magnitude here. And then the radius, they said, is 1.1. And so someone grab a calculator. Our minimum speed to make it around the circle is what? 3.3 meters per second. Sounds familiar, okay? Now, before we leave this question, let's do some comparison. What if my actual speed is less than the minimum? Think back to, the conditions of the loop-de-loop video that we saw. What if your actual speed is less than the minimum? Maybe I can demonstrate, right? And so here, maybe this is minimum. What if I do less? It falls out of the circle, whether it's straight down or wonky to the side. Okay, don't write wonky on the AP exam, okay? Okay, but if you're less than the minimum, it doesn't make the circle, does not make the circle. It falls out, okay? If you were riding a roller coaster without a seat belt and for some reason you were under the minimum speed, you would fall out. What if you were above? What if V actual is greater than the minimum? You'll stay in the circle, but what about our math? What about our equation would change? Now we would have tension. So tension would be greater than our zero. It would increase above zero. You would feel the tug in the string, okay? You'd still make the circle. Everybody would be okay. You would just feel more tug. If it's you in the car on the roller coaster, you would feel more pressure with the seat. Have you ever ridden a roller coaster and you're like, oh, I can't lift my head? You're feeling that, oh, something's pushing me out. No, the seat's pushing back on you because you're pushing on it. And so it's the pressure with the seat, that normal force. Everybody good with minimum speed? Okay, we call this a limiting case. It's one of the limits, okay? Now, B, calculate the tension in the chord at the bottom of the arc. And so I got my bottom free body diagram, force diagram there. To get an equation to find tension, step 2, I need to do what? F-net statement. So F-net C, because our object is moving in a circle. And just so we're all clear, it's at the bottom. So using the bottom force diagram, I have not identified positive, negative. Who's positive? Tension. Why? It's center seeking. Not because it's up, but it's center seeking. Gravity is negative. Why? Because it's center opposing, not because it's down. It's center opposing at that moment. And so our statement would be, I like to start with positive, so tension minus the gravitational force. We're solving for tension, so now I'm just going to do algebra. Let's isolate tension by adding the weight to both sides. And so I would get weight plus F net C, and that equals the tension. Now let's plug in other variables for the forces. Weight is still mg. F net C is still mac, which, just like we did above, becomes mv squared over r. So I did just skip a step. Is everyone okay with that? F net equals mac, and ac is v squared over r. So now, to solve for tension, we know the mass, we know the gravity, we know the r. But wait, the velocity, is the velocity at the bottom still the minimum? I guess I should finish reading the problem. Assuming the ball is moving twice as fast as it was the top. And so v at the bottom is equal to 2 times that it was at the top, which we found to be 3.3. And so 2 times 3.3 is 6.6. And so they told us, but not quite. And so now we know everything. We can plug in. Now it's just a math problem, right? Physics is done. Plug and chug. Mass, still the same. It does not cancel out when you solve for tension, right? Careful on the cancel. Don't get cancel happy. And so mass was given 0.15 times 10. I'm going to use, or you can use 9.8. Now, I guess I could have factored out mass, but it's fine. It doesn't save you many keystrokes. And then that new speed at the bottom, 6.6, don't forget to square, divided by r, which they said was 1.1. All right, so now get me the new tension. Remember at the top, we said it was 0 at minimum speed. At the bottom, gravity's been speeding it up as it goes from top to bottom. And you can clearly see we're going to get a number bigger than 0, right? $7.44. Is that what you said? Yeah. 7.44. Oh, not meters per second. What's our unit for tension? Newtons. So it's 0 at the top, 7.4 newtons at the bottom. Any predictions what it would be on the side? What would the tension be, relatively speaking? Well, don't exactly divide by 2. You don't know enough information for that, but it should be somewhere in between 0 and 7, right? Maybe it's half, maybe it's not, but it should be somewhere in between. It really depends on what the speed is on the side, which that's not given to us, okay? I would never make assumptions when acceleration is involved. Well, let me divide that speed by half or something. Don't do that, okay? But if we did a little ranking of the tensions, we would say the tension at the bottom is greater than the tension at the sides. And I'm going to say plural. Does it matter if you're on the right side or left side? No, tension's still center seeking, right? Same radius, same mass. And it turns out it would be the same speed on left and right side. And then the tension at the top. And one more thing before I leave this problem, looking at the side, what would your F-net statement read for the side? F-net C would equal what? Center seeking minus center opposing. It would be tension, still center seeking. Then what? Gravity's there. Is it center seeking? No. Is it center opposing 180 degrees? No, it's tangent. It's kind of not in the direction of your centripetal motion, okay? So that green dashed line there, gravity is not center seeking or opposing. It's tangent to the circle. It's just going to speed up or slow down the linear speed, okay? Okay, so that's it. That's all your F-net statement would be. No gravity in the statement. Okay, let's move on